Good afternoon everyone. Myself Sirsat Sonali Sirsat in Physics Department for S.V.K.T College, Devali Camp, Nashik. I am teaching the today's topic is the single phase alloy, the TYBSc Physics, Elements of Material Science, chapter number 2. Then first is the recap. This topic is the we was studied the previous lecture. Then the first chapter for the elements of material science is the defects in the solids. This points is the impurities in solids, solid solution in metals and its types, rules of solid solubility, imperfection in a crystals, defects in solids. Then defects in solids subpoints is the point, line, surface and volume defects. Next is the atomic diffusion, vacancy, interstitial interchange, mechanism. Next is the session agenda. We have studied the today's lecture is the single phase alloys, microstructures of single phase alloys. Next is the deformation. Next point is elastic deformation, plastic deformation and mechanisms of plastic deformation. Next is the learning objectives. First learning objective is the single phase alloy. Second is microstructure of single phase alloy. Third is deformation. Fourth, mechanisms of plastic deformation. And last is the critical resolved shear trace is called the CRSS. First point is the single phase alloy. In single phase alloy, an alloy is a substance that has metallic properties and it is composed of two or more chemical elements of which at least one in metal. Second is, in order to improve the properties of metals, another metal is added to it. Means another metal is the added the parents atoms or parents materials, then it is the impure materials and this call is the alloy. Such combination of metals in which one metal is added to another is known as an alloy. The alloying element present in a largest properties is called the base metal and all other elements present are called alloying elements. For example is the steel. Next is the properties of single phase alloys. First property is there is increases in a strength. Means for example is the steel. Steel is the increases the hardness for that the material. Means there is a increases in a strength and hardness due to the presence of solute. Second property is the electrical conductivity of metal is reduced due to alloying of elements. And third property is the atoms are interfaces with moment of atoms in a crystals during plastic deformation. Next point is the microstructure of single phase alloys, and this diagram is the single phase microstructure and dual phase microstructures. Then single phase microstructures is the change in size, shape and orientation of grains. Grains means the smallest particle of that the materials or atoms used to vary the microstructure of single phase alloys. The grains completely fill space and maintain in a minimum of total boundary area. Grain shape commonly depends on the crystalline orientation of grains. You know the crystalline structure is the BCC, FCC and SCPs. Next point is the deformation. Deformation is defined that the deformation is change in form produced by external forces that act on non-rigid bodies. Deformation is also longitudinal when it produces a change in length and angular when it changes an angle between various phases of solid. And then the type of the deformation is deformation is caused by two ways: mechanical action of external force, various chemical physics process. Following are two types of deformation. First type is the elastic deformation and second point is the plastic deformation. we have the studied for the, this diagram is the deformation for the trace versus strain. First point is the elastic deformation. You know the elastic deformation. The elastic deformation, for example, the rubber. Rubber is the stretched, is the external force is applied, then rubber is expanded, and then this force is removed, then rubber is also giving its original position. The elastic deformation is temporary because it is the deformation of a body which completely does not change the structure of materials. It obeys Hooke's law. When the material is forced, a temporary deformation of the crystals takes place through displacement of the atoms. When the deforming force is removed, the atoms return to their original equilibrium position and crystals recovers its original shape. Then tensile force applied to a single crystal tends to increases an interatomic spacing, while compression force tends to reduce it, resulting to increases of the energy with the lattice itself. Example like cast irons, silicate glasses show elastic deformation up to point of fracture, and copper, steel, aluminium shows elastic deformation up to elastic limit. Next point is, second is the plastic deformation. In plastic deformation is permanent because it is the deformation of body which remains even after the removal of external force from the body. Plastic deformation is the function of applied stress of or force, temperature and strain rate. When a metal is forced beyond the elastic range, it will never return to its original form due to flow of metal under the elastic deformation. It is accompanied by changes in both the internal and external state, and it is not reversible. Means the plastic deformation is the changes for the internal shape or size, but it not reverse to its original shape or size. Next point is the, this is diagram for the plastic deformation is the before loading. Next is the external force is applied. This is the material is the loaded, means stress, and next load remove, means load remove. Then this material is load remove, but this material is not the reverse in original step, your stage. Next point is the mechanisms of plastic deformation. Plastic deformation of a single crystal occurs either by a slip or by a twinning. Both slip and twinning occur by pure shearing. We have studied the only deformation by slip. Slip is a common mechanism. It is the mechanisms of deformation which represents a large displacement of one part of the crystal relative to another along particular crystallographic planes, and the preferable directions is called slip direction. There may be one or more slip planes and slip directions of each crystal. Next is the slip deformation is the diagram for the slip deformation. The slipping moment of a crystal planes is over a large interatomic distance. The atoms do not come back to their original position even after the removal of trace, as the atoms now have new neighbors. The slip occurs by translatory motion along the sliding planes and rotation of the specimen with respect to the axis of loading. This is diagram for the slip plane. Is the first diagram is the slip is the moment to the deformation for the plastic deformation. Next is generally the slip plane is the plane of greatest atomic, and the slip direction is the closest packet direction. Within the slip planes, the combination of slip direction and slip plane is called slip system. Next is the critical resolved shear trace is called the CRSS. Slip occurs when shear trace component parallel to a favorable oriented plane in the slip direction reaches a maximum value called critical resolved shear trace, means the CRSS. For each material, critical resolved shear trace is constant and depends on the type of bonding force. It is affected by temperature, surface effects, purity, rate of deformation, and extent of pure deformation. This is the diagram for the CRSS, is the slip direction, slip plane normal and slip plane. If normal force is Fn is equals to F cos theta, cos phi, shear force is Fs is equals to F cos lambda. Area of a slip plane is then As is equals to A0 upon a cos of phi. Then normal trace sigma is equals to Fn upon a As is equals to F cos phi divided by A0 upon a cos of phi. Then sigma is equals to F cos square phi upon a A0 is the equation number 1. The shear trace causes slip is equals to tau CRSS is equals to Fs upon a As, and then tau CRSS is equals to F cos alpha upon a A0 cos phi. Then tau CRSS is equals to, then solving this above equations is the F upon a A0 cos phi into cos lambda is the equation number 2, where cos phi and cos lambda is called Schmid factor. Lambda is angle between slip direction and tensile axis in above the diagrams, and phi is the angle between the tensile axis and the slip plane normal. Then case number 1, if phi is equals to lambda is equals to 40 degree, then TCRSS is equals to sigma upon a 2. It means slip and fractures. And case number 2, if phi is equals to lambda is equals to 90 degree, then tau CRSS is equals to 0. It means no slip and no fractures. Next point is the plastic deformation in polycrystalline materials. The plastic deformation in polycrystalline materials is more complicated than that of single crystal due to the effect of neighboring and the character of grain boundaries. Influencing factors, first factor is the each crystal is not free to deform as it is surrounded by other grain. Second point is the there is an added influence of grain boundaries, and third point is the each crystal has different orientation. Next is the stages in the deformation of polycrystalline materials. First stage is the under load. All the crystals are only elastically deformed. Second is the aggregates behave as perfectly elastic. Third point is the a few crystals pass the elastic limit and deform plastically. And fourth point is the plastic deformation in all crystals becomes considerable and there is appreciable yielding of aggregates. Next is the summary for this chapters is the single phase alloys. We have studied in these the lectures. Second point is the microstructures of single phase alloys. Third is deformation, elastic deformation, plastic deformation, and last one is the mechanisms of plastic deformation. Next is the assignments. Then first question is the define the following terms. Then first term is the alloy. Alloy means the mixing of the two materials or solute or solvent. Next the deformation. Next question is the next definition is the critical resolved shear trace. Second question is the what do you know about a CRSS? And precap is the molecular phases. And thank you.